Hi, everyone. I want to talk about matrix multiplication. The 3 blue 1 brown video does a good job of giving the idea, but I want to illustrate with an example and sort of show how the formulas for matrix multiplication come naturally out of composition of transformations. So let me write down a couple. Let me just start with an example. Write down a couple of transformations here. So let's do first, I think this was one that we had in a previous video. So transformation from R2 to R3, defined by following formulas. Um, 3x2. Okay, so that's one. Let's call that y1, y2, y3. But I also want to define over here another transformation from R3 back to R2. I'm going to have the inputs be y1, y2, y3. Let's do y1 minus y2 plus y3 and 2y1 minus 3y3. Let's call the output of that z1 and z2. So this is like we're composing functions. Right here we have x going to y, and here we have y going to z as vectors. And we can also rewrite these as matrix times vector, right? So we could also write it as, we could write TB of x is the matrix B times x, where B is the matrix whose columns are 1, 2, 0, 1, minus 1, 3, right? Just looking at the coefficients that we have here. And then similarly, TA of y is A times y, where A is the matrix. I guess the first row is 1 minus 1, 1, and the second row is 2. There's no coefficient of y2 here, so we have a 0 there and a minus 3 there. Okay? And the way I want to think about this is, well, what if we combine the two transformations, right? Like, what if we do, and we could actually compose them in either order, because one goes from 2 dimensions to 3 dimensions, the other goes from 3 dimensions back to 2 dimensions. But let's actually consider the composition. Remember, there's a symbol for composition, this little circle like that, right? So we could, by the way, think of this, maybe if we wrote it a little bit, we could write our, so we're doing, remember, you read function composition right to left. So we're doing B first and then A. So if we do B, we could write it this way, right? We have T sub B, and then we end up in R3, and then we do T sub A, and then we end up back in R2. So that's the composition. And we can think of that being, maybe I would say that that is a new transformation, T sub C, and then this is our T sub C is the one that goes sort of, that's going to be from R2 to R2 directly, right? But let's actually write it out, right? So if we want to think about T sub A composed with T sub B applied to the vector X, that's T sub A of T sub B of X, which is X1, X2, which is T sub A applied to, well, this formula, right? Because that's T sub B of X1, X2. So I'm just going to copy this right here. Probably faster just to just write it out. I could copy it, but x1 plus x2, 2x1 minus x2, 3x2. And we're gonna, what that means though, is that we're gonna basically plug each of these in for the y's, right? Like that's gonna go, x1 plus x2 is gonna go in for y1, 2x1 minus x2 is gonna go in for y2, etc. So let me just keep doing that. So it's gonna be y, so the formula up here is y1 minus y2 plus y3 for the first one. So I'm going to do this minus the second one plus the third one. Okay, so that's x1 plus x2 minus 2x1 minus x2 plus 3x3 there. And then the second row was 2 times the first minus 3 times the third. So 2 times that minus 3 times that. So 2 times x1 plus x2 minus 3 times 3x2. Okay. So what happens when you simplify that? You should probably pause and simplify it yourself. But I'll tell you what I get. I get minus x1 plus 5x2. All right, you should check that. And then I get 2x1 minus 7x2. Right, and so that goes from, and I guess that's our z1, z2 now. So we're sort of skipping the y's, or plugging in terms of the y's. Right, again, I could write this R2 is the x's, this R3 is the y's, and this R2 is the z's up here. So T sub C of x1, x2 is minus x1 plus 5x2, 2x1 minus 7x2. Like I said, that's z1, z2. But you could also say, you know, we could write this in terms of a matrix. TC of x is the matrix C times x, where C, if we just read the coefficients, are minus 1, 2, the coefficients of x1 are minus 1 and 2, right? And the coefficients of y1 are 5 and negative 7. So 5 and negative 7, like that. Okay. And so we have this new matrix that's associated to this composed transformation. And I guess the thing that I want to claim that C should be sort of naturally considered to be the product of A and B. Because let me just write this out, i.e., if we have T of A composed with T of B applied to X, by definition, that's T of A of T of B of X. And each of these, that's really A, you know, the transformation T is the same as multiplying by the matrix. Applying the transformation T is the same as multiplying by the matrix A. And then applying the transformation B is the same as multiplying, T sub B is the same as multiplying by the matrix B. And so, and then we just said that's the same thing as CX. So define, so this is the definition of matrix product. Define C to be AB, A times B, product of two matrices. This is sort of natural because of the way we've been writing everything so far, right? I think this is really okay. And let me just write this out really explicitly. Let me just write the matrices again, right? So I'm going to copy the matrices A and B. You know, A is here. In fact, maybe I can be somewhat clever. If I copy the matrix, this is A. And then if I multiply by b, so that goes there. And then I get c. And that's there. And let me put an equal sign in between them. So in other words, we're defining a times b to equal c, right? And you might ask yourself, okay, well, what are these formulas? There's a couple different ways to go about this. Like, how did we get, like, for example, you know, where does this like -1 come from? Like in terms of the numbers in A and B, where does this 2 come from in terms of the numbers in A and B? Right. So we can think about this. It's sort of interesting to take this thing and rewrite it, being super explicit about all the coefficients and everything. So let me actually do that just because I think it's a little bit instructive. It's maybe not the most direct way, but to see what's going on. Well, maybe it is. All right, so let me copy that down here. So remember, this was our sort of composed transformation before we simplified it, right? And I can rewrite this in certain ways, right? Like, let me just do something here. Let me just put in all the coefficients. Like there's a 1 there, there's a 1 there. I'm writing them in orange. There's a 1 there, there's a -1 there, etc. Actually, let me just rewrite it. So if we want to think about this super carefully, there's like a 1 times 1x1 plus 1x2. There's a -1 times 2x1 plus -1x2 plus a 1 times oh, this was supposed to be a 2. Sorry, right there, that's a typo. Should be a 2. This probably means it's a typo upstairs also. Yep, sorry, typo right there. That should be a 2. It's meant to be a 2 the whole time. Sorry if that was confusing. And so this was back to here, 0x1 plus 3x2. And then here we had 2 times 1x1 plus 1x2 plus 0. I'm going to put this very explicitly in here, 2x1 plus -1x2 plus -3 times 0x1 plus 3x2, right? I'm just recopying all of this, being super explicit, putting all the coefficients in very carefully. And the reason is you're going to rearrange, right? Like, I really want everything that's a coefficient of x1. And so we can trace the math here is what I'm trying to say, to sort of see where the formulas come from, right? Because if we rewrite this, we're going to have this, this expression, we're going to have 1 times 1, right? From like this x1 has a 1 times 1 coefficient. This has a -1 times 2, and this has a 1 times 0. So 1 times 1 plus -1 times 2 plus 1 times 0. So that's everything in front of x1. And you should try to do the same thing. Pause the video, do the same thing. And I'm just going to sort of copy out what I get. So I would pause and do the same thing for the rest of these terms. So right, if I keep going here, Okay, so the four the four numbers in the matrix C were these basically, and these are all from entries in A and B, right? So let me just be even super more specific. Let me copy this A times B again down here. So that's A times B. And we just said, if we just kind of write this all out very carefully, we get 1 times 1 plus negative 1 times 2 plus 1 times 0. As the top left entry of our matrix, 2 times 1 plus 0 times 2 plus negative 3 times 0, and etc. So that's the first entry. Second entry, I'm going to write these all out. Just copying everything again. Okay. And somehow, so you could try to see the formulas here, right? You might notice, these coefficients 1, negative 1, 1 came from the formula for T sub A. And in fact, there they are, 1, negative 1, 1. And then we have 1, 2, 0, which were the coefficients of x1 in the B matrix. And in fact, there's 1, 2, 0. So in fact, if you look at it, if we take this and we dot with this, we actually get that. So row dot column, right? This, maybe we could write it this way. This right here is row 1 dotted with column 1. What about the top right entry? I see 1, negative 1, 1 dotted with 1, negative 1, 3. 1, negative 1, 1, 1, negative 1, 3. So this is row 1 dotted with column 2. And I think you can check that this is row 2 it's weird, dotted with column 1, and this is row 2 dotted with column 2. So you actually see the numbers fall out. And so this is actually very similar to matrix times vector, right? If you just think about this vector and we wanted to multiply this matrix times this vector, we would do this row dot this column to get this entry, and then this row dot this column to get this entry. So this is this gives you sort of the formulas. It's just natural. It's sort of like the same thing we do with matrix times vector. Very similar to matrix times vector multiplication. We just do it for each entry or each column of the second matrix. Okay. One other way to see the same thing. So I'll just sort of point this out, that you can actually do this in a slightly different way, right? If we say, let's say the following. This matrix is B. This matrix right here is B, right? So let's label the columns, B1 and B2. Okay, then we can also we can write, T sub C of X, T sub A of T sub B of X. It's A times BX, right? And we could rewrite BX, right? We can rewrite the BX. If we think of this as, if we think of this as the matrix whose columns are B1 and B2 times a vector whose entries are X1 and X2, we can actually rewrite this as A times, remember the way that this works, X1 B1 plus X2 B2. And matrix multiplication distributes over addition and scalars. Like this X1 and X2 here are really basically scalars, right? So we could rewrite this as X1 times A B1 plus X2 times A B2. And then very similarly as to what we did up here, by rewriting this as that, we could sort of factor this as the matrix whose columns are AB1 and AB2 times the vector whose entries are X1 and X2, right? And this right here is C times X. So that equals that, which means that we could say, so C is the matrix whose columns are, we basically multiply A times the columns of B. So you also see this if you do some reading or exploring of like matrix multiplication. This is another way to think about it. Basically that we, yeah, that AB, I mean, really I should say, maybe I should say it this way. I should say that, i.e., if we want to think about A times B, we can think about it as A times the matrix whose, if we write the columns out explicitly like this, and then that's the matrix whose columns are like, so we basically multiply the first matrix times the columns of the second. So that's the other formula for matrix multiplication, but it's equivalent because I basically said that above. It's like we're multiplying the matrix, the first matrix times each column of the second. Okay, so this is one way you can see all the formulas for matrix multiplication. And really the best thing for you to do is to practice on examples. Like this example up here is nice. And there's more examples that you can find in textbooks and problems and stuff. Okay, so I will stop there.